Okay, well, it's time to get started with the rest of our talks for today. I hope everyone is ready. We've got a lot on deck. We're going to be making some spicy points. Okay, so I hope we're ready to get a little bit uncomfortable, get a little bit controversial, and have some really real discussions about where this field is going. So, for our first talk, we're going to be talking about kind of bioreactors again. When I say bioreactor, what do you think of? You probably think of steel tanks, or you think of airlift bioreactors, which is something you thought of yesterday, or you think about a lot of tubes and downstream processing and complicated scale-up and machine learning and optimized process control systems. But a cow is a bioreactor. I'm a bioreactor. You're a bioreactor. A fruit fly is a bioreactor. And so up next, I'm very pleased to introduce Dr. Matt Anderson Barrett, who is going to come up on stage and talk to you about fruit flies as bioreactors. And he's going to talk to you a little bit about what it's actually going to take to scale cellular agriculture and feed the US market. Future Fields estimates that cell ag will require 13,000 tons of recombinant proteins per year. But legacy bioreactor and bioprocessing models are energy intensive, time consuming, they require a lot of CapEx. Building all those steel tanks takes a lot of carbon emissions. Cleaning them out with steam takes a lot of carbon emissions. And so in a field that's all about taking animals out of the equation, Matt has taken the unconventional route of building an insect-based biomanufacturing company. And I'm very excited to welcome him to the stage today to talk to you a little more about that. Please welcome Matt.
Thank you. Thanks for the warm introduction. I'm really excited to be here today for several reasons. First, it's just so great to get the community all together, the cell ag community. We don't get to do that very often, or at least haven't been able to the last couple of years. Secondly, New Harvest holds a very special place in my heart. It's the reason that I got into Cell Ag. 2017 conference was my introduction to Cell Ag, and it's really cool to be here 5 years later and get to present. And lastly, I love that New Harvest is willing to address the elephants in the room, and I don't think every organization is willing to do that. So that's what I'm most excited about, is that we get to talk about all these really hard topics, because it's so important as an industry to address the hard problems. So coming back to the theme of the conference, the elephant in the room. We're kind of the elephant in the room, Future Fields kind of is. So like Kristen addressed in the introduction, we have a Drosophila-based biomanufacturing platform. So we genetically engineer Drosophila to produce low-cost, high-scale, sustainable growth factors for the cell ag industry. We call that the Ento Engine. And Drosophila are insects. Insects technically are animals. And New Harvest themselves defines cell ag as the growing of meat, milk, and eggs with cells instead of animals. So in a lot of ways, we are the elephant in the room. But that's not the elephant that I want to talk about. The elephant that I want to explore, at least initially, is what is the true environmental cost of growth factors for cell ag? If cultured meat and cell ag is climate tech, what are the environmental ramifications of deploying that at scale? And with that in mind, come back to trying to articulate why we've chosen to take this path, why we see Drosophila as part of the solution to the problems we face in cell ag. And with that, I want to start here. The reason that Future Fields exists, I think the reason a lot of cell ag companies exist, and that is to mitigate the effects of climate change, and to do that at a pace that actually can make a difference. A lot of the recent literature that's come out, including the latest IPCC report, has highlighted the sense of urgency that we have, how fast we have to move to stay below the 1.5 degree threshold. We need rapid deployment of technologies for decarbonization like cell ag. But we need to ensure that these technologies are actually going to be better for the environment. We need to do that analysis now, and we need to look at the entire supply chain, which for cell ag includes a lot of growth factors. And unfortunately, our industry has some significant environmental baggage. And by our industry in this context, I don't mean cell ag, I mean recombinant protein production. In fact, a study done by some researchers at McGill found that big pharma, which encompasses most of the world's recombinant protein production, is actually worse than the automotive industry for GHG emissions. And a lot of that is rooted in these legacy expression systems, yeast, E. coli, CHO cells. They all require very energy-intensive bioreactors, often have some pretty carbon-intensive inputs, and produce tremendous amounts of waste in the process. These systems have been around for decades, so they're more or less maxed out in terms of their efficiencies. And that's been fine for legacy applications in pharma and therapeutics, but with cell ag and the scale we're talking about here, that can be very problematic. You know, moreover, just from a business perspective for cell ag companies, the impact of Scope 3 emissions is becoming more and more acknowledged by regulatory bodies and large industry players. So if you're not familiar, Scope 3 emissions basically means everything involved in your process, including the inputs. So for cell ag companies, that would include the emissions associated with growth factors. And now this is compounded by this, what we call the second order infrastructure gap. You know, we know that cell ag is going to need a lot of these things, and we are currently not equipped to produce the volume that we need. We know that. This was highlighted in the counter article that we're going to dig into later today. But in the article, they talk about this gap in the infrastructure, which is 10 orders of magnitude. You know, cell ag companies are going to need massive amounts of raw materials, and a lot of that in the form of stainless steel for bioreactors to grow all these cells. We cannot afford to divert these precious raw materials to propping up the supply chain. If we need stainless steel in bioreactors for growing growth factors and for growing the cells, it's possible we'll just run out of stainless steel. The point is, the scale we need to grow to is pretty massive. And we need to think about that. We need to consider the supply chain in that as well, which includes growth factors. So how big is this scale we need to grow to? So we crunched some numbers to look at that. And we wanted to root this analysis in something meaningful. So we asked the question, how many growth factors would we need for cell ag to capture 10% of the US meat market? So after we did the math, and we looked at, okay, how many cells would you need to grow to meet the demand for 10% of the US meat market, which was 13,000 tons. So with that, we used information from the Cultivated Meat TA by Delft, which estimated about 41,000 liters of growth media for 3.08 metric tons of cultivated meat. We then extrapolated growth factor amounts from the BF9 formulation from Andrew Stout's paper, multiplied that by the volume of growth media needed to produce 1.23 billion tons of cultivated of meat, which is about 10% of the US meat market. And that gives us 13,000 tons of recombinant proteins. And now I want to acknowledge, there's some variability, obviously, in different growth media formulations. There's differences between growth media and differentiation media. But even if we assume a pretty big margin of error here, that's still a pretty massive amount. And to root that in something that you might be familiar with, insulin, probably one of the most well-known recombinant proteins produced, and one of the most ubiquitously produced around the world. In 2018, the global production of insulin was about 3.2 tons per year. So we need 4,000 times the global production of insulin to provide enough recombinant proteins for just 10% of the US meat market, never mind the global meat market. So again, even if our math is a little off here, we're still looking at a pretty massive gap in the supply chain. So that begs the question, where are we going to get all of these growth factors? We know that FBS is not an option. We know we need serum-free media. If cultured meat and cell ag is climate tech, FBS is not exactly clean nor environmentally friendly. So we look to recombinant technology to produce these. And with that, it makes sense to go with animal-free options because that is kind of the collective ethos of the industry. And animal-free growth media has existed for a long time, well before cell ag was around. So why is that? What would prompt the production of animal-free growth media in absentia of cell ag? If we're going to get 13,000 tons of this stuff, we should probably look into these things. So it's helpful to kind of reflect on where the term animal-free came from with respect to growth media, and that is mitigating against the risk of spongiform diseases like BSE, aka mad cow disease. So when the source of this disease was discovered, it was implied that disease transmission from species to species could occur simply by exposure to an infectious protein or a prion. And this drove a sense of urgency to innovate and develop animal-free growth media, especially for biomanufacturing. The risk of transmission of BSE was far too great. This is the etymology of the term animal-free with respect to growth media. But it was likely never meant to imply an organism's location on the evolutionary tree, but rather as a quality control term to mitigate against the risk of using traditional animal agriculture byproducts in biomanufacturing, especially for therapeutics. Now, we have seen, and obviously acknowledging our bias, we've seen this term propagate into the field of cell ag, with media development teams anchoring to the term animal-free, when the collective ethos might more appropriately be framed as traditional animal agriculture byproduct-free. We're concerned that if animal-free for growth media is the default choice, we are defaulting to a path dependence on the production systems that produce animal-free components. And as we dug into this number, this 13,000 number, we were surprised to learn the implications of industry-wide use of animal-free components and the serious energetic and GHG costs of those. And those costs may actually outstrip the benefits of cell ag with regards to the environment. So given that we can estimate the volume of growth factors that we need to produce, we can also estimate the environmental impact of those growth factors. So to start, we used what's probably the workhorse of recombinant protein production, E. coli, probably the most efficient of all bioreactor-based systems. And so based on existing LCAs for bioreactors, we calculated the GHG, the carbon emissions associated with biomanufacturing of recombinant proteins in E. coli, which we estimated about 110 million kilograms of CO2 per kilogram of recombinant protein produced. That's based on the average US energy grid, and I should note it does not take into account the massive carbon emissions associated with mining, manufacturing, and shipping stainless steel for the bioreactors themselves, so not necessarily a cradle-to-grave approach. Now, if we are to couple this number, 110 million kilograms of CO2, to the demand for recombinant proteins to feed 10% of the US meat market, the environmental impact is staggering. About 26 times the current anthropogenic carbon emissions globally. 26 times everything that we're currently producing for carbon emissions, every single industry. This, in our opinion, is the big elephant in the room that we need to talk about. If this is the unintended trajectory that cell ag is on, we're concerned that by confusing the colloquial term animal-free with regards to growth media for marketing purposes with the quality control term, there may be some serious environmental impacts when cell ag is deployed at scale. Now I want to come back to the other elephant, which is us and our Ento Engine platform, and talk about why we're okay being the elephant in the room. So if cultured meat and cell ag is climate tech, we believe that it is, and we take environmental impact very seriously. We wanted to apply that same sort of analysis to our own production system and look at the GHGs associated with it. So based on our own analysis that we've done in-house, we calculated our carbon emissions associated with producing recombinant proteins in our Ento Engine platform would be about 13,400 kilograms of CO2 per kilogram of recombinant protein, about 8,200 times less than an E. coli system. This is why we built the Ento Engine, to meet the needs of cell ag, which isn't just about cost and scale, which is kind of the common thread that everyone talks about, but it's also about the climate needs. It's about creating a low carbon supply chain, and that's especially for growth factors because we're going to need so many of them. This is why we're not just okay being the elephant in the room, we're very proud of it. Now, there's other benefits to our Ento Engine platform, and I don't want to turn this into a pitch where I'm talking about the benefits from cost and scale, because again, everyone talks about that. I want to focus on the environmental impacts and the environmental benefits of our system, which again, I've talked about the efficiencies of it. It's a low carbon method to produce recombinant proteins. But we also have the added benefit of basically being waste-free in all of our upstream production. So all of the residual biomass that we produce that's left behind after we've purified our growth factors can actually be used. It can be valorized and turned into other high-value products. For example, we just developed a method to extract chitosan from our residual biomass. And chitosan's a really cool molecule. It has tons of applications in tissue engineering, in wound healing, wine filtration. It's a natural antimicrobial. And actually, I just learned yesterday about some applications in textiles for chitosan. Insect manure, which is called frass, actually makes a really good organic fertilizer. It's a biostimulant for plant growth. And fertilizer is really important to think about with regards to our food chain because we use so much fertilizer to grow plants and grow crops. And we know that a lot of the methods of chemically synthesizing fertilizer through things like the Haber-Bosch process we know are quite horrible for the environment. So moving to organic sources of fertilizer is really important to think about as well. So we have this added benefit of basically taking our waste, or what would be considered waste, and turning it into high-value products, which again is in stark contrast to bioreactor-based systems, which instead produce a lot of liquid waste that's actually very challenging to deal with. So now I want to touch on the ick factor that I'm sure is on some people's minds, the fly in my burger. I think it's important to consider what we're producing here. These are growth factors. They are not ingredients. These are processing aids. They don't become part of the final product. Most, if not all, growth factors interact with the cell surface receptor, and then they're degraded shortly after that. And growth factors, unfortunately, have very short half-life, so that process actually happens quite quickly. Not to mention, these components are purified from the host material before they're added to growth media. So, just like a diabetes patient is not injecting a fecal coliform into their body when they're administering their insulin derived from E. coli, right? These things are purified. So just as there would be no E. coli in your burger, there would also be no fly in your burger. Now lastly, just to kind of wrap up here, the key to good science is debate, and it is the peer review process. So we have an article penned that basically digs into everything that I talked about today, including all the calculations and basically how we came to these numbers. And we're planning to publish that in the next couple weeks, I believe. And when we do, we invite scrutiny to all of those ideas, all of our thoughts, all of our calculations. Because again, that's the key to good science, and we recognize that we're not going to always get everything right the first time. So when that article does come out, please take a look, and if you think we're wrong about something, please let us know. So that is something that we take very seriously is looking at these hard problems, talking about them, and gut checking us. And we kind of hope we're wrong, at least partially. But if we are right, even partially right, then cell ag is facing another major challenge that I don't think a lot of people have thought about. Now, we're not saying we're the only solution to this problem, but I do believe that we could be a big part of it. So if there's anything that we've learned over the last 24 hours of panels and talks, and probably the talks that are coming today, is that there are multiple elephants in the room. And elephants are hard to talk about because they challenge our optimism. But elephants are communal creatures. They live in surprisingly complex social structures. And just like elephants, cell ag is a community. We are all here today, literally in one room, to talk about and address these big problems. And no matter how big the elephant, no matter how big the challenge, we're here, Future Fields is here to help work on those problems. You guys are all here to work on those problems together because, hard problems are worth solving. Thank you. Happy to answer any questions now.
Thank you so much, Matt. That was awesome. Gives us all a lot to think about, right? We should just jump right into it. And I think my first question isn't dissimilar from this first question, but I'm going to jump in first. I think one of the things that I think about a lot, and I brought this up, some of this got brought up yesterday, is about communicating to the end customer. So as you're communicating to customers of your growth factors, what would you say to customers who want to use that product to convince them and ultimately their customers that this is safe and ethical? One of the things that comes to mind is, the debate around GMOs. We generally think GMOs are safe, but not everyone does, and there are some challenges there.
Yeah, on the note of safety, first, just to quickly address that, we take that very seriously. We've already done some pretty rigorous safety testing on our products. I think that's an advantage we have that I didn't really touch on, is that, Drosophila are inherently non-pathogenic and non-hazardous. In fact, if you look into it, there are a certain number of whole fruit flies you're allowed to have in a packet of raisins. And that's considered safe, and I think it's like 5 or 10 or something like that. So there's clearly very little concern about consuming insects from a safety perspective, and there are billions of people around the world that eat insects as part of their daily diet. And anyways, we do very rigorous safety testing. We include that in our COAs. On the note of the ethical issue, and it's not ridiculous. It's not ridiculous to ask that. We think about it all the time, and we take it very seriously. We've consulted with ethical insect advocates, and we've consulted with philosophers and people who think about these things. And and there's some debate about whether insects are capable of suffering, and we just take the approach that yes, they are capable of it. So in our practices, we ensure that whatever we're doing, we are minimizing any potential suffering that might be occurring. And actually, one of the key indicators of the key measure of insect unhappiness is escape behavior. If they're clamoring and trying to get out of their cage, and oddly enough, we can open our cages and they just chill. They're fine. They're happy. And I think that's another strong argument for insect agriculture as a whole, is we're creating environments that insects love. And that's not the case for industrialized agriculture for cattle, right? Cows don't like to be in small pens. In contrast, insects love dark, dank, crowded places, tons of nutrition, no predators. Our our fruit flies live a glorious life, especially compared to the ones that are out there in the field getting hit by insecticide and pesticides that are used to grow soy crops for things like tofu. So these are things that we do take very seriously, and we do try to integrate into our production practices.
I love that point. It's like fruit flies don't necessarily like the things that we like. I like this question too. We've brought up sort of the idea of molecular farming. How does this compare to recombinant protein production in plants? And I think you can take that question in any direction, from a cost perspective, from a greenhouse gas footprint perspective, however you want to take it.
Yeah, we have looked at molecular farming as well in some of our analyses, and first of all, I think it's a very cool idea, and I think there is a lot of value to that. But I think the problem is, with respect to cell ag, we can't just think about what might work at a particular scale. We need to think about the numbers that I was talking about earlier, the 13,000 tons number. That's the frame of reference we should have when we think about systems that might work. And I think the big challenge with plant systems is they grow too slow. Plants grow way too slow to make this work. You need a lot of land mass to grow transgenic plants to feed the growth factor needs. Our calculations, we took into account the best reported yields in a plant system ever for growth factor expression, and looked at how much land would you need to supply 13,000 tons per year. It was a land mass the size of Lebanon, right? That's how much land you would need to produce the growth factors for the cell ag industry. So I think that's a big challenge with plant systems, is just how slow they grow, which means you need a lot of land. You can only harvest those crops, I think some of them, like tobacco plants, every 100 days or so. So I think that's a big challenge with any of the molecular farming, is that you just need so much land, and you can't really do that in a greenhouse because you're short of space, and the energetic cost would be insane to do that volume in a greenhouse. So not to mention, doing it in infield crop production, you're reverting to monoculture, which is horrible for the environment, but also you're putting your supply chain at the whims of the climate, which we know is very fickle. You have floods, you have droughts, you have pests that will just destroy your crops, and then your supply chain is gone. So those are the kind of challenges that I think we need to consider when we decide, okay, this is going to be a solution to this really big problem.
Yeah, you've just pointed out one of my favorite elephants in the room, which is the question of all of the inputs that are going to be needed for cell ag. One of the things that I like about Future Fields platform is the possibility to use waste streams and sort of plug into a circular economy in that way. What do you make of the idea that companies might eliminate the need for growth factors? This came up yesterday also, and so I'd really be interested to hear your take on that question.
I think we kind of need to approach it from both angles. I guess from my perspective, my understanding is that we'll never eliminate the need completely. I think there's ways to reduce the needs tremendously, so we don't need as much. But I don't think there's a way to completely eliminate them altogether. So I think it's important to approach it from both angles. That approach to basically reduce the amount we need, in combination with creating systems that are better equipped to produce the volumes that we need. So I think both approaches we need to do simultaneously.
Okay, that makes sense. I think we have time for one more, and this is one. This might be a question that you can't solve on your own, but I'm interested to hear your perspective. So if greenhouse gas emissions are so staggeringly high, if the energetic and GHG costs for growth factors alone are so bad, does this not imply the same for cultured meat itself, or that it's orders of magnitude worse ultimately?
Yeah, we've thought about that. I think the important thing to remember is what is being produced in these bioreactors. What I was referring to was producing molecules in bioreactors. So the mass you're getting out of them, the amounts you're getting, are significantly different than if you're growing entire cells. So the outputs are very different, and because of that, the economics, the GHGs, are very different as well. So I can't comment too much on the actual LCA around cultivated meat production. I think there's been a few that have been done. But I think that's the key distinction between what I was talking about and ultimately a cultivated meat LCA is what is coming out of that bioreactor. Cells or molecules, and cells are way bigger than molecules, obviously. So that output is different, the economics are different, and the carbon emissions are going to be different as well.
Matt, thank you so much.
Thanks,
This
everyone.
was awesome.
Thank you.
Just pass off to Kevin. Thank you. That was awesome. I really love that we're now starting to dig in and really think about this from an LCA and climate perspective. And I hope some of you will go find Matt and ask him more questions.